Good afternoon. I'm Subashisa, Professor from IIT Guwahati. Am I audible to all? Or good afternoon. I'm audible to all. I can start. Okay. So good afternoon all. I am Subashisa, Professor from IIT Guwahati, and really I welcome to these live sessions for the mock course on fluid mechanics. So in these sessions, we'll be just discuss about briefly what we have covered or what is the issues in generally we encounter when you have a fluid mechanics problems. That's what is my idea. Then we'll be coming back to the live sessions, or you can post the queries and I will try my level best to answer your query. If you look at the fundamentally this course, what I have designed it is looking aspects of both mathematical aspect of the fluid mechanics as well as the physics part or conceptual part of the fluid mechanics. That is the reasons the book of Sinjal Simbala book, which one of the very clear-cut concept as well as the mathematical part is there. So that's what the reference book or textbook is considered in this uh, course of mock course of the fluid mechanics. If you look at the FM White book, which is very standard book on the fluid mechanics, but these are not having this number of examples, the figures, illustrations, not as compared to the Single Simbala book. And the same's also the part of this. So this is the standard book which we have followed to prepare this fluid mechanics mock lecture components. Now to look at most of the things what I introduce it, which I believe it slight bit different than this. If you look at that, we need fluid mechanics, we can have two approaches. First approach is Lagrangian approaches. That means in that viewpoints, we track the fluid particles. The number of the fluid particles, we track it. We at the look at there how the positions are changing that at different times. So as we have a n number of the fluid particles and we track it, and we can conceptually or easily understand it that each fluid particles has the velocity, has the accelerations, has the flow energy, it has the kinetic energy and the potential energy. So we can easily understand when you make it the fluid flow problems in a Lagrangian view. But the problems comes is that it is very difficult to have a understand it the total fluid flow when you go for Lagrangian view, because it has to have a number of the points the fluid element to consider that to that is what the anomalous. That is the reasons most of the fluid flow problems we go through the control volume concept. That is what emphasizes that. But the students can easily understand the Lagrangian form. But when you come to the control volume approach, somewhat we lost the Lagrangian concept part. So the virtual fluid ball, just integrating that, we were solving the problems in the Eulerian framework only, but we try to look at how the flow is coming. What is the inflow? Where is the outflow? What is the directions of the flow with respect to the control surface? All the things we can characterize as a concept of virtual fluid balls. That's the reasons I put it as a virtual fluid balls. I know this is a new concept, but you just try to understand it. If the students are particular problem when you are solving it, you should always have an idea that the flow is going on or the flow at the rest. That means all these properties, virtual fluid balls are all at the rest conditions. So basically the flow, to understand it, we should use the virtual fluid ball. The idea as extended and look it that way, as I told it, that if I have a, I have a solid structures like this, and I have the uniform flow. And if I mark the three particles, these particles will be moved like this. So these particles I'm considering as a virtual fluid ball. So that way it can go like this, go off like this. But the particles which is moving it, which is virtual fluid ball one, that as soon as come to the structures, there are the no slip boundary conditions. That is the reasons here the fluid particles will not move with the same velocity. So that has to be reduced, and there will be a formations of boundary layer. To represent that flow reductions, the flow velocity reductions near these structures, we try to conceptual as a virtual fluid ball. That means this ball can disintegrate it into a number of the balls. Then the disintegrated balls can try to move with a different velocities. So that is what the concept, that we can zoomify it, we can zoom the part, we can look at how the properties are going to change it. Conceptually try to understand it. Same way, if you look at this fluid element 3, which is virtual ball 3, can move like this. So basically, always the students should draw the streamline, draw to try to understand if the flow is going from the left to right, there is a substructure, how the process will be changed. How the streamline patterns will change. These understanding is more required as compared to the only this mathematical versions of the control volume concept. So that's the idea about these codes, and that is what we try to throw virtual fluid ball the students to encourage to visualize the flow, how the flow is happening, how the streamline pattern would be there, how the path line patterns will be there. At which are the critical zones within this, like as I'm discussing, this is the critical zone near the structure, near this flat solid body. So that understanding should be there by the student. More detailed the boundary layer formations and all things, no doubt I have covered in the class, but the students should have an understanding that flow is patterns, how it's moving it. If they consider as equivalent, they have n number of balls and they are moving with different velocity. They try to interact each others, as well as they try to integrate or disintegrate depending the conditions. That is the reasons this virtual fluid ball concept was introduced. Now, if you look at that, many of the times we should try to understand the nature of the flow velocity, how changing it, because that understanding can help us to consider whether the flow is a three-dimensional nature. We should consider it, or we should consider two-dimensional or the one-dimensional. That the variability, the students should understand it. Like for examples, near this flow, we have the bigger pipe connected with a smaller diameter of pipe. So if you look at it, when this flow at these locations, you will have a three-dimensional velocity components. Okay, if I have a cylindrical coordinate systems, this three-dimensional velocity variations can define as r, theta, and z. But once that entrance is over, if you look at it, it doesn't depend upon the theta. It depends upon only r and the z variations. So z in these directions. So it doesn't depend upon the theta direction. Further, if you go it, then you will see that velocity, the distributions are not changing with z direction. That means at these locations, the three-dimensional velocity field is required to define how the flow process are happening at this point. At this point, we need a two-dimensional velocity. At this stage, we can consider the one dimension. So this understanding is necessary. It is not that how have to approximate the flow. Okay, with relative importance. That is what you have to try to understand it. That's what again I'm repeating it. If I have a I have a VR, V theta, and Vz. Always we should look it in the relative sense how the velocity variations are there. But if you look at this BR is 3 meter per second, this is 0.1 meter per second, and Vz is 0.005 meter per second. So if you look at these magnitudes of the velocity, you can easily say that I don't need the Vz value because as compared to related to Vr and V theta, Vz is much smaller components. So that means I can solve this problem as a two-dimensional problem. So that is what, so you have to do the relative analysis, magnitudes analysis. This is what to be encouraged to students to look at the problems and visualize the problem, which directions have how the velocity variations are there. It is not easy to understand very beginning, but as the students will solve many of the problems, they can try to understand that which are the components I consider, which dimensions I can neglect it, and which dimensions I should consider. That whether one dimensional or two dimensional, or you need to consider radial and longitudinal directions, all you can understand it as you try to understand the flow process and their magnitudes relationship. This is what the microscopic point of view, the fluid as a continuum. I think I'm not going more details because it's not supposed to be a class here. Please try to know it that whenever you have a fluids, there are microscopic uncertainty will be there and macroscopic uncertainty. There are no questions as raised in forum, so I'm not discussing it. But please try to understand when you have a microscopic uncertainty, your molecular motions, that what is responsible for mass and momentum exchange, they play much major role. Okay, that's what it happens. That's the reason if you take a limiting volumes, you don't have a certainty. This value can varies considerably. Okay, so after these limiting values, so you will have the densities, which is a basic properties of the fluid flow, is mass per unit volume. Then we have a macroscopic uncertainty, which I discuss in the my presentations. So basically what we try to do it that we make it the fluid fields, for examples of the pressure field, the velocity vector, accelerations vectors, all are a continuous functions. So that's the continuous functions. That is what the basic idea. And on these basic assumptions, we try to solve these basic fluid mechanics problems, whatever we address in our. Now I not going much about systems and control volumes as I discussed in the class. But if you look at that, the control volume can have a different natures. It can have a movable control volume. It can be a fixed control volume, or it can have a deformable control volumes. As if you look at uh, this is the fixed control volumes. Okay, you have a nozzles. You define a control volume like this. This is the moving boundary control volume, or it's a control volume which is deformables with time. The 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 size of the control volumes are changing with the time. So those things you can have, and few of the examples we have solved using this. Next thing, as you know it, as I try to summarize, I try to look at that fluid mechanics problems we can solve. Either first method is experimental, which in general in fluid mechanics we don't textbook, we don't emphasize it, but that matters lot with a scale models. You do a testings, you can get all this velocity field, pressure field, and density field, because that is very important to understand how the fluid flow process are happening, how the velocity variations, pressure variation, density variation. There is no doubt in this course we emphasize more in analytical approach, where we try to know it the gross velocity field or gross pressure field, gross density field, not detailed velocity field or the pressure field density. So that is the reasons we use a control volume. We apply the basic equations of mass, momentum, linear momentum or angular momentum, energy conservation flow. This is what integral approach. Or we can go for last, which is recently famous more, okay, numerical computational fluid dynamics, where we try to solve series of partial differential equations to get approximate velocity field, the pressure field, and the density field. This is what also I discuss in the. So these are the things you know it, the flow pattern, streamline, path line, and the streak lines. And most of the time the students are confused with that. What is the difference between the streamline and path line? If you look at that, you have to look at what is the definitions indicating. And I think the streamlines, the concept what is we have developed through a steam tube, which is help us to simplify a lot of fluid mechanics problems. That's the reasons we use so frequently the streamline, because in the streamline at a given instant of the time, okay, at given instant of the times you want to draw a line, draw a path, anywhere you take it, that's the tangent should represent the velocity vectors. Okay, the everywhere tangents to the velocity vectors. That means if I draw a line, a path, at this path, whenever I have draw this tangent, that's what is the directions of the velocity vectors of that location. What does mean that there will be no flow across this. Okay, there will be no flow across the streamline. That's what visualize as a steam tube. So the concept of the steam tube simplify our analysis, because there is no mass exchange, there is no momentum exchange through the steam tube. This surface, only these two surfaces will have a mass exchange and momentum exchange. So the streamline concept, if you try to look at, uh, we try to use that the same concept for the derivations of Bernoulli's equation, simplifying the many problems. That is the reasons we use the streamline concept, which says that at any given instant, that means you can have an unsteady or steady flow. If you draw a path, that path will be show you the tangents to the velocity vectors. Okay. The path line and streak lines, as you definition says, that it's quite easy to understand it. Now, if I look at the questions array, I think this is quite relevant questions We got it from there is slight bit confusions in the sign conventions and the problems what we solve in Ganga and Brahmaputra. There is a slight bit mistake is there in the sign conventions. Okay, but let be clarified that see when you try to look at what could be the sign conventions, we always define the control surface. Always define the control surface. Okay, control surface. Draw the perpendicular to the control surface. Okay, draw the perpendicular to control surface. Then I have the velocity factors. Okay, let me I have the velocity vector like this, which is making 180 degree. Okay, this is my control surface. Flow is inlet. This is the inlet condition. Inlet condition. So it's a making a 180 degree with respect to my the perpendicular vectors of control surface. So when I do a V dot N dot product analysis, that means I have a V cos theta. That means V will be negative. Theta is 180 degree. Just reversely if you look at, this is the inlet condition. For the outlet conditions, we will have a V dot N is V cos theta. The theta is angle between the normal vectors and V. That's the reasons will be V will be the positive. Theta is a 0 degree. So please try to do the solve the problems looking at the RTT. What is your normal vectors and the dot product of the V and N. Okay, that V and N, that what will be giving us the signing, it will be negative or the positive. Okay, but somewhat the problems what we have, there is a mistake is there in terms of negative, but I think with a due course we'll try to correct that part. Okay, otherwise if you try to understand it, you just draw the control surface, try to look at the perpendicular to control surface and your velocity factors. What is the angle is making it? Is it a 0 degree or it's a 90 degree, 180 degree? So based on that, you can find out whether it will be negative sign or the positive sign. Okay, so that way you can define the mass flux and the momentum flux component. Okay. There is a question too, due to the molecular mass momentum flux actions, why does the layer A velocity reduces and layer B velocity increase, not the vice versa? I understand V2 must be greater than V1. I'm asking that is there any particular reason why it is happening like this? Okay. Please try to understand it that when we have a fluid flow, I'm considering very simple examples. I have a plate and I have uniform flow. Just try to understand. So you have a plate and you have a uniform flow of velocity U is coming. As this no slip boundary conditions here, the velocity is supposed to be 0. The particles which are connected to the fluid particles which are connected close to the surface, as this is a fixed, you should have a velocity equal to 0. So that means there will be velocity gradient. That's what we can observe it very microscopically if I measure the velocity. Okay, so if I measure the velocity, I can see that this uniform velocity distributions will change it. The velocity will be 0. Then velocity depending upon different what type of boundary layers and all. So the velocity distributions will change it, which I can measure it and already reported this velocity distribution. Now, if you try to look it at a microscopic level, that means if I take a smaller stretch, very small element, and in that element, I have a 2 layers. Okay, let me, this is V2, this is V1. Okay, so there is a velocity gradients are there. Why it is happening? If I look at microscopic point, molecular motions are there. Always the moleculars are going off, coming down. So there are the exchanges, molecular motions are there from one layer to other layers. The momentum flux, mass flux is going off and going down. Similar way, this momentum flux is going off and going down. Both the processes are happening. It's not that, but effectively, because this velocity V2 is moving it, this is a V1 is moving it. So you can try to know it that there are the stress is developing because of exchanging of this moment. So that's what the shear stress is developing. Shear stress is developing, which is proportional to velocity gradient and all. So if there is no velocity gradients, the basically what you will try to make it, the V2 for equilibrium case, V2 will be tends towards the V1 value, or V1 will be tends towards the V2, so that after certain time V1 equal to V2. That is what the hypothesis I try to explain it. So you try to understand when you have a microscopic there is a mass flux is going on, momentum flux is going from top also mass and momentum. The net results, there is a shear stress formations are happening between these two layers. So basically the shear stress part will be reduced to the zero as the velocity both will be the same. Both will be the same. So that is the reasons they will be equilibrium, or they will tending V2 will be tending toward V1. V1 also will tend towards the V2. The microscopic, if you look at this molecular mass exchange are happening, it momentum exchange are happening, it that what is resulting as a shear stress formations within these two layers. That is what we try to explain it when you look at the microscopic view of fluid motions. Okay, that what we try to understand it, to try to know it. There is a mass, molecular masses, the new mass is there and moment of flux is there. Because of that, these processes are happening. Okay, so I think that is what I explained same way. We use the virtual fluid ball. Okay, thank you. ऑडिबल था तो I was audible, na? Hello. Any questions? Yes. They can chat, no? Yes, you can chat the questions if you. Yes, there is no questions. No. जब प्रेजेंटेशन दे रहे थे क्लास Any questions, please? Just interact with me through chat or as well as you can. Oh, okay, okay, now. Any questions? Any feedback about this fluid mechanics course? Any questions? Shall we close it or continue it? There's no questions. Basically, I'll tell it that this course is designed at the intermediate level. So bringing a lot of illustrations, even if laboratory components to encourage the students to understand the fluid flow conceptually as well as mathematically. That is what my idea. And it's quite success in terms of number of students registered so far in this course. In the chat. सुनाई दे रहा था बीच में था सब है ना नहीं है तो नहीं जब शेयरिंग टू अनशेयर आया ना तो उसमें थोड़ा सा कुछ प्रॉब्लम हुआ लग रहा है Say, please chat your questions. This is an interaction hour, but I just try to explain few things. I'm audible. Am I audible or? 50 minutes later start. As there is no questions, so we'll just wait for another 1 or 2 minutes to close this interactive session. Just 1 or 2 minutes. question. Right? What?
जो शेयर ऑन सेट टाइम शायद नहीं हो गया माइक ऑफ
On set, of course.
माइक ऑफ हो गया लास्ट जो
Last few minutes only. Two minutes were. Okay, so there is no questions with this. Let us conclude this session. Thank you all whoever attending this interactive section. Thank you.